Welcome to a lesson with Dr. Powell. In this video, we will take a look at how Mobius matrices help count what is new. Okay, so let's look at an example of something that a Mobius matrix could help us with, all right, in this way. So let's make a poset diagram that right here, it's a Hasa diagram for this idea of 2, 10, 5, and 1, but in such a way that this is going to refer to something. So the see this 10 right here, we'll think of a 10 multiples of 1, 2 multiples of 5, 1 multiple of 10, 5 multiples of 2. It looks like we're looking at the numbers from 1 to 10. And amongst those, there's 10 multiples of 1, 2 multiples of 5, 1 multiple of 10, 5 multiples of 2 in the numbers 1 through 10. So we're taking a look at all the numbers 1 through 10. 10 represents all the numbers 1 through 10. 2 is some of them, 5 is some of them, 1 is some of them. All right? Now, if we were to put question marks for nodes, thinking of the bottom parts as being sums, cumulative sums up to a point, then these questions tell us something. They tell us what is new beyond what we've already considered. From multiples of 10, if we go up to multiples of 5, what's new? Well, there's going to be one multiple of 5 that's not a multiple of 10. So the node will be 1, and that's what we'll get right there at that point. So maybe we can write that out. Okay, so let's write in, if we have just thinking about that. So at the bottom we can think, well, the node will be, there's one thing to count, so that's a 1. At this point, there's one multiple of 5 that's not a multiple of 10. Okay, right here, multiples of 2. Well, there are 4 multiples of 2 that's not a multiple of 10, namely 2, 4, 6, 8. I mean, the number 10 was already counted down here. Here, to be precise, the number 5 is, extra 5 is being counted. Now up here, there's going to be 10 things total, but there's some things haven't been counted yet. We haven't counted 1, nor 3. We've counted 5, 6, but we haven't counted 7. And we also haven't counted 9. So there's 4 things up here that have not been counted yet. So, see, 4, and we have 4. But notice the total sum up to this point, 4, 4, 1, 1, actually will be 10. Okay, so the node, the question mark, is what is new beyond what has already been considered down below it. We could even make a matrix, a Mobius matrix for this particular poset, and then run these sums through. And if we did, let's see. Okay, so we have this as our Mobius matrix, considering specific ordering. All right. The ordering that we're using in this case, and notice how I've highlighted the top row. Maybe that's because I'm interested in something. In fact, it looks like I'm interested in the top number. I'm interested in obtaining this top 4, so I was only looking at the top row of the matrix. Because if you're thinking of a row interpretation multiplication of matrix multiplication, if you run through the particular sums that we have, namely 10, 2, 5, 1, and we'll end up getting exactly what we computed here. So 4 for the 10, 4 for the 5, 1 for the 2, and 1. So let's see. We have 4, 4, and then we had a 1 and a 1. And we can double check the matrix multiplication to see if this is the right matrix here, that ordering. You see, notice, yep, I get a 1 there. Yep, I get a 4 and 1. Yep, it looks like it's correct. Okay, so, but if I want to get the top row of the result, the top row of the result comes from inputting the top row right here of this matrix into this column, thinking of this column as being like a function or something like that. Okay, so we end up getting, we can get that, and that's what this computation is. So specifically, if we're looking for one thing, maybe we could focus our efforts on just figuring out what a row is of the Mobius matrix. And that's a common technique, is just looking for a row, especially if it's like a top sum. Like, what's new at the top is often a question. And then that would help us figure it out. Now, really, what are we computing here? This actually has a nice meaning here of what we're actually doing. We're considering the numbers 1 through 10, and the number at the top is thinking, okay, what are all the numbers that are not multiples of 5, multiples of 2, or multiples of 10? Meaning, pretty much, notice that 10, 5, and 2, those are the non-trivial factors of 10. We're trying to say, does anything share? We're trying to find how many numbers don't share common factors with 10, is what we're trying to compute. That's what's new. The new thing at the top here of this poset, of this lattice right here, this divisor poset or divisor lattice, is precisely just the number of things 1 through 10 that don't share factors with 10. Hey, that's the Euler phi function. Phi of 10, that's actually what it computes. It computes the number of integers 1 through 10 that do not share a common factor with 10, and we get that as 4. So actually, this is a top node solution, just kind of and there's a Mobius matrix which can actually help us with that. Let's look at another example of thinking what's new. In particular, if we are if we want to look at something like this, this right here, and let's take a look in at it a little bit. What's happening here? We want to compute maybe the size of a union of sets. Okay, we have a set A, a set B, set C. What's the union of? Well, we know what the size of A is. A is going to be 3, B is going to be 4, C is going to be 2. But their intersections have different sizes. And then not only do their intersections have sizes, but the triple intersection also has a size. How can we work with that? All right. Well, so what we're seeing here is actually sums. It's kind of like the sum, here, and this is the sum. But maybe it might be, and then if we answered the question, then if we looked at nodes, we'd be thinking about what is new. Well, it's interesting to note what's new at the top. What is new at the top? At the top, actually, is new 0, because all the points of A, B, and C have actually been considered up to that point. So we can automatically actually know that the top node here is actually going to be 0. That's going to help us when we try to answer the question. We have a missing sum, but we actually know that the top node is 0. Let's try to just think about the top node for a minute and how we could actually get that in a how we can actually get that in a calculation. Okay, so the top node, let's just think about what standard basis vectors would do. The standard basis vector that has a 1 at the bottom, think about, and for sums and everything else are zeros. Think of how you would actually get that for your nodes. Well, 1 here, -1, you could just kind of work through it. I'll just kind of write over that. -1, and up here at this level, okay, so this has a negative 1, 1, a negative 1, and a 1. So to make this 0, I would need a positive 1. Similarly here and here. Okay, 3 1s, 3 negative 1s, and a 1. I better have a negative 1 here. So it looks like the contribution of this standard basis vector with a 1 at the bottom and zeros everywhere else actually yields a negative 1 node at the top. So in the Mobius matrix, suppose it's like E1, where would it go? At the top, you would have a -1. If you had E2 going up, actually similarly, kind of a little diagram, what if we started with E2, thinking about where that would go? So if we started with E2, thinking of imagining that was E2, what would the contribution at the top be? Well, we have a 1 where we kind of think about this a little bit. We have we're going to have a sum of 1 right here, a node of 1. This node will have to, all the other nodes would be, all the other sums are zeros. So we'll have a negative 1 at that point to make a 0, negative 1 at this point to make a 0, because these could be zeros as well for the nodes. So I'll just concentrate on this upper portion. And then right here at the top, it looks like we're going to have a positive 1 right there to make a sum of 0. So it looks like for the destination of E2, if the sums were E2. I mean, this particular case, remember, is a specific case of sums that we're working with. But in order to get the matrix and know kind of what the top row of the matrix are, we look at the individuals' sum calculations. So E1 has a contribution, like we said, of negative 1 at the top. So we're just looking at top contributions of each of these. So to build the top row of the Mobius matrix, the top contribution of E2, it looks like it's going to be a positive 1. And notice as we move up, it's going to alternate. So from here to here, we're going to have 1s at this level. The next level will have negative 1s. And at the top, we're going to have a 1 alternating. So, so in this case, this could be like the top row of the Mobius matrix. And then from there, you simply can plug in what you plug in these sums. And in particular, when you plug in the sums, what is this going to be computing? It's going to be computing what's new on the top, because we're just taking the top row. And we know that the result will be equal to 0 when we matrix multiply this row with the column that corresponds to here, the way I've ordered this at least. So E1, okay, I guess is first position really is denoting down here. So I guess 1, and then I guess went 2, 1, 1 like that, 2, 1, 1, 3, 4, 2, and then I have a question mark here. Run the so I run this calculation, and I would be able to compute that. So here's a slide, and I don't know if I use the same ordering, but similarly we can kind of think about it. Notice though what's happening here is, okay, this is the level right down from the so if you look at the levels, this level right here, right down from the top. And notice that the contributions from this level, so if we think about the contributions at that level, I just said that's what that represented, those negative 1s. And we can review that if you want, the contributions at that level. So if we have like a standard basis vector with a 1 at this level and zeros down below it, we're going to have a negative 1 at the top. So negative 1 contribution to the top. So we can think that level gets, notice, right, so that we have the contribution of well, right here, aha, the calculation, top node is 0. All right, right here, yes, from that level we get negatives. From the next level we get positives. Okay, and the bottom level we got a negative contribution. Top level was a positive contribution. So notice this line right here is actually, you see these things, these are the sizes, these are the sums, but then they have pluses and minuses attached to them. And that is simply due to that, to a matrix product where you have a row of negative ones and positive ones multiplied to a column vector with these sum sizes. All right, and the result should be equal to 0. Of course, we can solve for this by moving everything else to the other side, and then the signs flip. Okay, that's what that was. And then we'll end up getting 6 in that computation. This is also known as inclusion-exclusion, but it works, but we can also think about it in terms of Mobius matrices and counting what is new. Okay, here's another example of counting what is new. Here, if we're taking a look at the sizes of so permutations. So permutations on 3 things. To keep this kind of basic. So permutations on 3 things. And the number of permutations on 3 things is right here. Total number of permutations is 3 factorial on 3 things. What if we take subsets of 1, 2, 3? Permutations on this subset is, there's 2 factorial of those, so there's 2 things, a set of 2 things. Subsets of size 2, subsets of size 1, subset of nothing, 0 factorial. There's 1 thing you can do on it, do nothing to nothing. 0 factorial is equal to 1. So we end up getting, a way of, we get a post set like this, but we want to think about counting what is new. All right, permutations at the top, which do not correspond to permutations that are only on this set, meaning anything outside of this set is fixed, like 3 doesn't move, but 1 and 2 are swapped maybe. Or, it doesn't correspond to anything in here or here. Something new up here that's not a permutation on things like this, meaning the permutation doesn't fix anything. Like there's no 1 cycles. There's no 3, there's no 2, there's no 1 cycle. Okay, so we're looking for everything that has no 1 cycles in it. I mean, for here, that's called a derangement. It has a specific name. It's a permutation that doesn't have any 1 cycles. So it doesn't fix anything here. So for instance, on 3 things, you can think, well, 1, 2, 3 does that, but also 1, 3, 2 does it. And try as you might. So let's think. Let's see if that's right. Are there 2? Well, let's try to figure that out, because the number of derangements is going to be the it's going to be counting what is new at the top node that hasn't been considered by anything down below it. So it's kind of like it's answering the question mark. It's finding the node if these are the sums. Now in the previous example, we actually had the exact same post-set structure. So the contributions at the top will be the same. From the bottom here, it's going to be a -1. From this level, it's going to be a +1. From this level, -1, and this level is just going to be 1. Those contributions going up from the bottom to the top. All right. In particular, we can look at some solutions here. So this is a sums. So if this right here is a sum, this is a standard basis vector. These are the nodes solutions, and we're concentrating on the top thing. So the bottom level gave a contribution of -1, and right here we can see that this is the sum right here. These are the nodes. So notice that this guy at this level gave a contribution of +1, and it'll alternate as it goes up levels. This is always true for a post set structure, such as this right here in this case. Okay, so moving along, let's take a look at that and see what this might look like. So we plug in the sums, and we have the top contributions from all the standard basis vectors. So this would be the top row of the Mobius matrix is right here. We matrix multiply this and run through, and that computation yields, as we desired, the number 2. Okay, or right here I just kind of wrote these in. This is the number of things at each level, actually. 3, 0. Number of things at the bottom level is 1. Things at the level right above that is 3. Things above that is a 3. And here, this is notation. This means 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So you could write it that way as well. And this -1, +1, -1, and +1, those just represent the entries from the top row of the Mobius matrix. We're having a lot of fun with this one post set. Let's see another example on this exact same post set. We've already kind of seen the structure of the top row of the Mobius matrix, so why not look at something else we can do with that same top row, that same Mobius matrix, has the same structure. So, and we'll end with this one. All right, so we're going to let this right here be the number of functions that have their range, or actually just that have where their range is included in the set 1, 2, 3. So that includes sets that have their range so all the outputs of the function are in 1, 2, 3. If the outputs of the functions are in 1, 2, then they'll also be in this set of functions. Or, if the outputs are in 1, 3, they'll be in that set, and so forth. So you have things like this, and maybe we're interested to know what's new at the top. What's new at the top would represent the number of functions that have, what's new at the top would represent functions that can't be considered of anything down here. So everything must be hit, 1, 2, and 3. In other words, it'd be a surjective function. Now, if we fix things a little bit, so we're looking at a specific domain, and perhaps the size of the domain is 5, we could do a little counting. We could count how many surjective functions there are from D to C, with domain of 5 and a codomain of 3. We can actually figure out how many surjective functions there are with that characterization, because that's going to be counting what is new at the top. Well, first, maybe we should figure out the sums. How many functions there are from a specific domain, and we fixed this domain at 5. Okay, so that's fixed. So it's one domain. We're not going over all different domains. We fixed our domain. It's a specific set, and this specific set has 5 things in it. Also, we'll specify C as a specific set. Say it's a set 1, 2, 3. We want to know how many surjective functions there are from D to C. Okay, so we need to count these guys. And when counting those guys, we actually have some very nice numbers here in the computation for those things. Thinking about, we have 5 things that need to be put places, right? And they can be put anywhere. I mean, they just need to have a destination. So let's suppose that, so we have 5 things, 1, 2, 3, 4, 5, and how many functions go into the set 1, 2, 3, having 3 options? Well, the first guy, there's 3 things it could go to. The second guy in the domain, it can go to any of the 3. It doesn't matter if it goes into something that's already been taken. It doesn't matter. You can have a constant function across. It's fine. So there's 3 options for each. You multiply those together in pairing those different possibilities, and you end up getting 3 to the 5th. Similarly, 2 to the 5th, if you have 2 options you're only considering for that you could be sent to, things could be sent to on this level, and so forth, so we can count that. Now at the bottom, thinking about that, what's 0 to the 5th, you might think, okay, if the codomain there is no codomain, right? I mean, it's the empty set. Well, so guess what? There's no functions, right? Because everything in the domain has to go somewhere in order for it to be a well-defined function. So it should make sense. That's 0 to the 5th. There are no functions that take us to a codomain of nothing because it has to go somewhere for it to be a well-defined function. Therefore, we have these as our sums. And then see these pluses and minuses, pluses, minuses? That just comes from the top row of the Mobius matrix, if you will. And if you plug it in and put it in, you will get 150. So, lots of things can be counted on a post set. This is just some things. In the next video, we'll actually go to a different post set. We've kind of stuck with this post set for a few times, but we'll look at another one and see some other things that we can do. Thanks for watching.